Alright, so this chapter 12 on pressure vessels is from the Strengths and Materials book by Mott and Untener. And we're going to study it here as being relevant to mechanical engineering profession, particularly those taking employment in our area and in Texas. There are very many applications of pressurized pipes and vessels in the oil and gas industry, in the oil refinery. So you can have various tanks shapes, that is the way they end, but the main part of them, they are cylinders. They're also spherical storage tank for liquefied natural gas. I mentioned pressurized pipes to transfer fluid, as well as submersibles, submarines. They can also be analyzed as pressure vessels, where the outside pressure is higher than the inside pressure, but something that is not discussed here. Okay, so we care about finding the stresses and condition of failure for these pressurized vessels, spherical tanks and cylindrical tanks, because we want to select the material the right way and satisfy design factors, required design factor, which are subject to standards and code regulations. Boilers too are pressure vessels, by the way. Okay, so whether you cut section a cylindrical or a spherical tank, and in case of spherical tanks, you slice through the center, you're going to recognize 3 diameters, or 3 and 3 radius. So there will be the inside diameter, the outside diameter, inside radius, outside radius, as well as the mean diameter. There is the wall thickness, also shown on this graph. And I warn you, this is where students do mistakes invariably. Some students not paying attention what relationship exists between the inner diameter and outer diameter. So you subtract from outer diameter, the inner diameter gets you twice the wall thickness. Okay, if it's just radii, subtract from outer inner radius, you get the thickness. Okay, so don't forget to divide by 2 when subtracting from outer diameter to inner diameter. The mean diameter is going to be, of course, outer diameter plus inner diameter divided by 2, or is going to be the inner diameter plus thickness, or the outer diameter minus thickness. Alright, so please pay attention. The analysis that we'll be doing are based on 2 sets of equations, 2 assumptions based on the proportion of the thickness of the wall to the overall size of the diameter radius of the tank. So we call a tank thin wall if the ratio between the mean radius and the thickness of the wall is greater or equal to 10, or diameter over thickness is greater or equal to 20. If it is less than 10, this ratio, or less than 20, diameter, mean diameter over thickness, that pressure vessel will be assumed to be thick-walled, and we're going to use different equations to capture the type of stress distribution, radial stress distribution, which otherwise for thin walls it's assumed to be constant throughout the cross-section. An approximation which is valid again for these cases, but for thick wall, the approximation made are no longer true. Okay, so for spheres, in order to find the stress on the walls of the sphere, we're assuming again a section through the center of the sphere, not offset, and by doing so, and it could be in any orientation as long as it's through the center, and of course the wall is assumed to be even throughout. So collecting the pressure over the projected area, which is the inside diameter squared over 4 times pi, that's the area of the projected, and you multiply by pressure, gets you the force that is needed to hold the 2 half sphere together. So say I have a 2 half hemispheres, and I glue them. The glue that holds them together is subject to a force that is equal to, and here they are shown 2 forces, but there's just one force, the resultant of the forces, which is the pressure times the projected area, the inside, that is the inside ring, that's that inside diameter squared over 4 times pi. Okay, so that resultant force divided by the area of this annulus, this ring, it's going to give us the stress into the wall cylinder. And how do you get the area of the annulus? We're taking the mean radius and we multiply that by, or rather the mean circumference, pi mean diameter over 2, or rather pi times mean diameter, or 2 pi times mean radius, and multiply that by thickness. It gets us the annulus radius, or the area that is the area of the material that is loaded axially by the resultant force. And again, it should be just one force somewhere here in the middle, but not 2 forces shown. Or that force is distributed and give or generate the tensile stress. Okay, so this is actually, it says here for thin wall, but no, for any, this is, they still have it here. It's true, this equation is true for any thin wall or thick wall cylinder, so it'll be pi over 4, and then you have outer diameter minus inner diameter times outer diameter plus inner diameter. The second is going to you divide this or split this into 2. So outer diameter plus inner diameter divided by 2, that gives you the mean diameter, and then outer diameter minus inner diameter divided by 2 gets you the thickness. Okay, so not just for thin wall. And this is what I said directly. It's one of the, I think it's Papius-Goulden, one of those theorems, and I stated this first. So you take the mean circumference and you multiply by thickness, and gets you the areas of the annulus. Okay, so what is the resultant force caused by the pressure? The one that's, remember, 2 half hemispheres that or glued together. What is loading that or stressing that glue layer? So resultant force is pressure times projected area, and then the area of the annulus, we agreed upon it. So the end result is pressure, side pressure, times mean diameter over 4 times thickness. That's the stress in a thin wall sphere. And as you can see, I said earlier that it's inner diameter of the projected area, it's considered to be the mean diameter instead. Anyway, this is the first equation to remember. Allows you to calculate the stress in a thin wall sphere. So make sure firstly that the sphere is thin wall, and allows you to calculate the stress. For a thin wall cylinder, Things are a little bit different because we have a difference in geometry, longitudinal geometry and transverse geometry. So for longitudinal geometry, the analysis is the same as for, doesn't matter how the cylinder ends, any shape, it will be just a projected area, and the longitudinal stress will be the same as for the stress, the tangential stress in a sphere. All right, so following the same steps, the resultant force, and then that force divided by the area of the annulus, we get for the what is called longitudinal stress in a thin wall cylinder, same equation as for tangential stress in a sphere. If we move to the transverse stress, which is also called hoop stress, so imagine you're cutting longitudinal the pressure vessel or cylinder, and you take the projected area multiplied by pressure. So projected area is going to be the length of the cylinder times the mean diameter, work with the mean diameter of that cylinder. And then that force, so again, projected area times pressure gets you the force. That's imagine now the cylinder being like two halves longitudinally cut that were glued together. What is the stress in the upon the glue? We take that force length. We don't need to know, and we'll see it simplifies out. So length times mean diameter, that's a rectangle, times p, and then we divide it by, so that's force, divide the length times thickness taken twice, because we have this area and this area of the material that gets stressed. End result is the hoop stress or transverse stress, hoop stress of the cylinder, and as you can see, it's pi mean diameter divided by 2 times thickness. So it's, instead of 4, it's 2, which means that hoop stress is twice as big in a cylinder. So the hoop stress is twice as big as the longitudinal stress, which is equal to the tangential stress in a spherical tank. And it shows that a spherical tank makes better use of the material than a cylindrical tank. So the plus it's a better use of the shell material to fabricate a spherical tank. That's a different story, but it's important. So same amount of material for a cylinder and used to fabricate a cylindrical tank or a spherical tank. The spherical tank will take most volume, plus the stress, or maximum stress, will be only half for the equivalent. And we need here to recognize that assuming the same diameter. Okay, so there are some sample problems that you want to follow. The key is, again, to recognize that in order to apply the earlier equations, 1 and 2, or maybe the hoop stress and longitudinal stress or tangential stress for spherical tanks, you need to first check that the tank is thin wall. If it's not thin wall, the approximation made that the stress is about even through the wall is no longer valid. For a thick wall pressure vessel, so the stress distribution is having this shape. It's parabolic and it's maximum to the inside. Okay, so either the hoop stress or tangential stress in a thick wall sphere, it's not constant, but rather varies parabolic. assuming a thin wall cylinder, let's say have 1, 2, 3, 4, 5 times thinner, the wall, the variation will only be this much, and it can be assumed to be constant. But for thicker wall, again, we need to account for the substantial difference between the minimum, maximum, and an average stress, which would correspond to the early equation. So let's see how we deal with this. The book provides, without any justification, provides a set of equations that could be useful to calculate the hoop longitudinal and as well as radial stresses in both or in thick wall cylinder, as well as tangential radial in the thick wall spheres. There are new notations introduced to make these equations simpler or more manageable. So instead of inner radius, we use A. Instead of outer radius, we use B. And then the inside pressure is going to be P. And inside pressure is going to act normal to the inside surface and creates a compressive stress to an element that's to the inside. On the outside, it's atmospheric pressure that's assumed to be 0. Okay, so again, read carefully what A and B are, identify them for your problem. There will be essentially inner radius and outer radius. And then the equations, first or second column, first column of equations gives you the stress at any radius between A and B. And as you can see, the hoop stress is function of R. Longitudinal stress is not function of R. Okay, and then the maximum stress for longitudinal stress is the same even throughout the wall. And then the maximum stress for hoop stress is, in case of thick wall cylinder, it's to the inside surface. Remember that figure that I or diagram with hyperbolic distribution of stress presented earlier. Parabolic, why? Because we have power 2 here. Radial stress starts with maximum value to the inside, compressive stress, and equal to the inside pressure, and to the outside we'll just get to 0. So if we have R equals B, this becomes 0. Okay. Usually we care about the stresses to the inside, and we care about stresses to the outside. For spheres, the tangential stress, it's also maximum to the inside surface. You just make R equals to A, and then the radial stress likewise varies from maximum compressive to a 0 value to the outer surface. The analysis, it's relevant because to the inside is relevant because we have less or the quality of the finish is less, and he can also have corrosion starting from the inside, and analyzing not just the outside but rather the inside, and of course this is where the maximum is are relevant. What the design procedure is, repeat myself, so make sure you use the right equations. If it's thick wall, the thin wall equations will give you the stresses is calculated with the thin wall equations. For thick wall cylinders and spheres will give you less stress. Here is bigger, the thicker the wall is. Anyway, so we want to limit the design factor. by an amount n, or rather the design stress by an amount n over the yield strength. Usually 4 is the recommended design factor. Sometimes we relate it not to the yield strength but at the ultimate strength with a design factor of 6 instead. And then if we have pulsing, that is pressure that is pressure that is a tank that is emptied and pressurized multiple times, design factor should be 8, and again with used with the ultimate strength. Okay. The chapter continues with sample problems. There's one that I projected earlier. Remember, it requires again sample problem. So it plots the hoop stress distribution in a thick wall cylinder, and the variation is shown. So you can see between the outside and inside, it's about what close to 30% variation in difference in stresses. Okay, so before we look at Mohr circle, this is where Mohr circle gets interesting for actual practical problems that we can calculate the stresses and look at the maximum shear stress. Let me project it because I do have some let's see, and it says pressure vessels. I have some photographs. So remember the hoop stress in pressurized pipes or pressurized cylinders. Let me project this first. It's twice as big compared with the longitudinal stress. And as you can see, this was a drawn cylinder, and it burst. It burst in a longitudinal. This other one shows us two things. That shows us that again the hoop stress is bigger than the longitudinal stress. It could have instead, if they were equal but they are not, could have burst next to the weldment, either here or on the other hand. So I said two things to observe here: that the hoop stress is bigger than the longitudinal stress in a pressurized cylinder, and also that the heat affected zone, so you had sheet metal that was welded, and right next to the weld the material was weakened by the welding process, and that's why it burst next to the weld rather than elsewhere. Okay, unless there's some defect, but again the strength of the material was compromised by all the welding process through recrystallization. Maybe it was cold rolled sheet metal, and it burst, as you can see. And then I do have toroidal tanks are not discussed in let's see if it's, hopefully it's recording. New codec, not now. Okay. Yeah. So with some other occasion, I'll play this video showing a test done by NASA to their toroidal tanks. They used to store liquid fuel and oxygen for their rockets. Okay, so let's go back to the chapter and look at these Mohr circle exercises. Okay, so for a pressurized cylinder, the longitudinal stress is half of the tangential, the hoop stress. The corresponding Mohr circle will be like so. So I have the hoop stress, I have the longitudinal stress. again, 1 is half, sigma 2 is half of sigma 1. Here's a need for a thick wall, for a 3D Mohr circle analysis. We add sigma 3 equals 0. It's the outside pressure on the surface of the cylinder. Maximum shear stress, it's only now revealed if you work with a small circle. This would be RNO, so the material actually experiences this much maximum shear stress. Okay. For a pressurized thin wall sphere, imagine sigma 1 and sigma 2 are equal, sigma y and sigma x are equal. They are also principal stresses. So there will be just one point, the Mohr circle, and the 3D circle is the one that goes through 0. You can refine the analysis and look at what happens to the inside, and this will be shifted in the negative realm. But it's where usually thin wall tanks and pipes are subject to less pressure than the thick wall ones, and you can again account for the normal stress to the inside, and this point is actually going to shift to negative values. Okay, an example where analyzing the stress at an angle other than the so a pressurized vessel, a pipe, longitudinal and transverse direction are principal directions. You have the principal stresses, but you want to calculate the stresses on an element that's aligned with certain direction. And here's the case of a welded tank made of sheet metal, helical, twist or shaped and then welded. And we have an angle given. We have the pressure to the inside. We have the wall thickness, and we want to calculate the shear stress at some angle. So with all the information given, you calculate longitudinal stress and tangential hoop stress, which would be twice as big. This is the principal element already. There's no shear. Knowing that there's no shear on the sides of the element means there's it's a principal element. And we can draw the corresponding Mohr circle. We have sigma 1 and sigma 2. We draw this 2D circle. If we want to calculate the stresses at an angle that is rotated, so we need to look at the figure. Of course, we can rotate either 65 degrees or the element. So we rotated 65 degrees, and it has to be well, it's like going the long route. So 25 degrees rotated counterclockwise will align one side of the element with the direction of welding, with the helix on the side of the cylinder. So it's what they did. Now on the Mohr circle, so again 25 degrees counterclockwise. On the Mohr circle, we need to rotate in the same direction but twice the angle. So on the Mohr circle, we have the Mohr circle. We rotate 2 times 25, it's 50 degrees, and this will be the direction on the circle, orientation on the circle of the element that is has one side parallel with the weldment. And the intersection of that line with the circle gets us the two the stresses on the two faces of the 2x2 opposing. This is W and V directions, and we can extract them, and the corresponding shear stress is going to be the elevation. We project to the tau axis, gets you tau VW. All right. So we have sigma V, sigma W, tau VW, and with the knowledge from our book, the chapter 4 on combined stresses, we can calculate the maximum shear stress. Let us not forget we have so this is only 2D circle. If we want the maximum shear stress, we need to account for that third principal stress, which on the outer surface is going to be 0. More on how to blend various sections, half a sphere with a conical section, visitation. In chemical reactors, they have flanges or visitation openings, sometimes transparent. Things happen over time. It can corrode, pressurized vessel can corrode to the inside, depending on what you're storing. For example, hydrogen storage is problematic because it can do hydrogen embrittlement to particularly to higher grade steels, not the softer one. Oxygen oxidizes the surface, inside surface, and acetylene gets stored, dissolved in acetone, and there's a porous material to the inside. So it's area of study by itself. Sizing pressure vessels. We look to the basics. In the problem that just to practice on real cases, not just made up sigma x, sigma y, tau x, y values, but rather coming from careful analysis. We're going to look at pressurized pipes that are also subject to bending and torsion. Again, in addition to the stresses induced by pressure. Regarding the equations to use, there's no harm. There's no statement elsewhere, but I'm telling you, if you use the thick wall formula for thin wall cylinders, there's no harm done. The other way around is problematic. If you use the thin wall equations with thick wall cylinders or spheres, again, because we have this substantial changes in stresses as we move along the radius. Okay, so this is about it. I'm going to using the document camera. I'm going to go over some numerical problems together with you. Although before that, not to make it a separate recording, this is only 33 minutes. Let me show you the, and I'm going to share the with you the spreadsheets that this spreadsheet that I created. And this is on Mohr circle, and so what it does, it generates the Mohr circle for you. Of course, in an exam situation, you're not allowed to use it. The exam will be in class. You can, of course, check your work with the spreadsheet, but they're actually, to my knowledge, and I'm going to look and see if I can find, to my knowledge, there are some nicely done online apps that do just that, the Mohr circle. So I'm on the on page 157. 157, I said 57, and let's draw the Mohr circle with the spreadsheet for the same problem. So again, very straightforward. X and Y stresses are given. and the shear stress are given, and we need to calculate the principal stresses, maximum shear stress, and the angle, as well as the orientation of the principal element relative to the stress element. Okay, so I have the book in front of me, page 157. I'm looking at sample problem 4.3, and put these numbers in the spreadsheet. As long units are not stated anywhere, as long as you're consistent, you don't mix pascals, megapascals, and psi with ksi and so forth. Everything's good. So I have here sigma x, it's 10 ksi. I have sigma y, it's negative 4 ksi. Sigma z is not specified, but you can have it other than 0. Again, if you do analysis to the inside of a thick wall cylinder and you take into account the normal, the inside pressure, they'll occur here as a negative number. And then tau xy, it was 5 ksi. So 10 ksi, negative 4 ksi, sigma z 0, and tau xy 5. And it even says where the x-axis end is. The okay, so we have sigma x, sigma y, tau xy is 5. So if you project this 5 and 5, we're at the 5 here, tau xy, this will be negative 5 tau yx. The diameter of the circle, the center of the circle, which is the average stress, is 3. And so same as in the book. And then principal stresses now. I have sigma 1, 11.6, same as in the book. Sigma 2, it's negative 5.6. I have maximum shear stress, the radius of the circle. You just project this, the top of the circle, I think it's called quadrant, on the y-axis, the tau axis, and it's 3. Minimum value is 8.6 plus. Negative 8.6 will be tau minimum. And also calculates the equivalent, assuming this to be a ductile material. Calculates the using sigma 1, sigma 2, and sigma 3, which sigma 3 being so sigma 2 is 0, sigma 3 is will be this value. Okay, and it's a 3D Mohr circle figure. Okay. Although the 2D circle is enough to calculate tau max, and the orientation of the principal element relative to the stress element is you need to rotate clockwise half this angle, and half the angle would be 17.769. So this angle is twice as much. That would be 35-ish. Okay. So Mohr circle exercise. We're validating my spreadsheet with the book, or the vice versa. We can do also with the spreadsheet problem, sample problem 4.6. So I have 10, I have negative 2, and I have negative 4. So one more time, I have 10. No, this is 0. Sorry, and this is negative 4. Okay. So this time, to get from the stress element to the principal element, I need to rotate, to go on the part, I need to rotate counterclockwise this much. So half of this angle, if I'm to measure it on the, I move it until these look very close to circles, I can measure this angle, although it's calculated, we have equations for it. Von Mises stress, and will be sigma 1, sigma 2 0, sigma 3 listed here. Okay. What else? Okay, let's assume a spherical tank. I said that tangential stress is the same, 10 and and 0. Let's see how Mohr circle looks like. So Mohr circle for a spherical tank, the 2D circle is right here, it's a point. The 3D circle, it closes through 0, which is the normal pressure on the outer surface. If you do this analysis, say for a thick wall pressure vessels, you may have here, let's say, the two, I don't know, I'm just making it up, and by the way, it has to be negative, it's inside pressure. And so again, the 2D circle is just one point with the negative pressure or normal stress due to the pressurized, the inside pressure. This is where the circle is shifted, and I can tell the maximum shear stress would be, in our case, in this case, 6. Okay. There's ambiguity about, since there's just a point, the orientation of the principal element. Actually, the principal element, irrespective of how I rotate it, remains principal element, because tangential stresses in a spherical tank remains the same, irrespective of orientation. In case of an exam situation, I'm going to supply you with the thick wall cylinder formula for sears and tanks. If it's the case of a thin wall, you have them here. So for thin wall cylinders, the equations are provided here. Okay, so we're going to stop here. There will be some numerical problems that I'm going to solve using the document camera. It's actually my cell phone being attached above my desk. Alright, well, thanks for watching. Enjoy the rest of your day.